Our first speaker of the afternoon is Georgia Benkart from University of Wisconsin-Madison, who will tell us about fusion rules.
Thank you, Erhard and Michael, for creating this wonderful diversion to everything that's going on. So it's been great. So I'm going to talk about fusion rules. What you should be thinking about here is tensor products. And the story that I want to tell, it goes back kind of to ancient history, to the Makai Correspondence, which is really the inspiration for what I'm going to talk about. So John Makai was doing a lot of experimentation with computers, and he took the simple modules for a finite subgroup G of SU2, and he took the natural two-dimensional representation of SU2, tensored it, and decomposed it into simple modules. So these numbers here, these MIJs, are just the multiplicities. And out of the MIJs, he created a quiver. So this quiver has MIJ arrows going from I to J. And if you have an arrow going from I to J and an arrow going from J to I, then you just replace it with a solid line. To make the adjacency matrix of the quiver, and I'm going to refer to that as the Makai Matrix. And what he noticed was that the Makai quiver in this setting is really an affine Dinkin diagram of type ADE. And if you take this Makai matrix and subtract 2 times the identity matrix, subtract it from 2 times the identity matrix, you get an affine Carton matrix of type ADE. So the marks that we usually see on the affine Dinkin diagrams are really the dimensions of the simple modules, the SI for the group. And Makai also noticed that that's an eigenvector, and the eigenvalue is 2, which is the dimension of V. Another way to think about it is it's this null vector for the affine Carton matrix. So the nullity of the affine Carton matrix is 1, and this vector of dimensions for the group actually spans the null space. So here's the picture. So these are the affine Dinkin diagrams of type ADE. There are 2 infinite groups, families of groups, the cyclic groups of order n and the binary dihedral groups, and they correspond to type A and D. And then there's the binary tetrahedral, binary octahedral, and binary icosahedral groups. So the pink node is what we're tensoring with. And in all cases, it's one of the simple modules for the group. But when the group's a cyclic group, all the representations are one-dimensional. And so it's a sum of 2 of those. The affine node, the blue node, is connected to the thing we're tensoring with, and that corresponds to the trivial module for the group. So when you tensor it with the V, you just get back V. So once this Makai correspondence became known, sort of the floodgates opened, and everybody was finding the Makai correspondence, you know, sort of behind every door and under every rock. And one of the early papers was this paper by Steinberg. So, of course, the Makai correspondence now is related to all sorts of things, orbifolds and singularity theory and so forth. But this early paper by Steinberg dealt with groups. So what Steinberg said was, why don't you take just any finite group and any finite dimensional faithful complex G module with character chi V, and take the characters of the simple G modules, tensor SI with V, just like Makai did, form the Makai quiver, just the same way, and the Makai matrix, which is the adjacency matrix of the quiver. And then one of the things Steinberg proved was that, in fact, the dimensions of the simple modules form an eigenvector for the Makai matrix, and the eigenvalue is the dimension of V. But actually, he went a lot further, showed that if you take the characters and you evaluate them at any element of the group, you get an eigenvector. Now, this could be 0, and of course, there's a lot of repetition because characters are traces, and traces are the same on conjugate elements. So, in fact, the columns of the character table are the eigenvectors, and conjugacy class representatives give a complete set of right eigenvectors. So if you think of your character table, the rows are labeled by the simple modules or the simple characters, and the columns are labeled by conjugacy class representatives. So you just take a column, that'll give you an eigenvector, and you look at what conjugacy class that corresponds to, representative, and you just evaluate the character of V on that class representative, and that's the eigenvalue. And I think what's interesting about this is that the eigenvectors do not depend on the V. They're the same for tensoring with any module V. What depends on V is the eigenvalue. So I should say something about this word faithful up here. This just ensures that as you take repeated tensor products with V, you end up with all the simple modules. Now, you don't necessarily have to assume faithful. It's just that then your quiver will not be connected. We'll have connected components, but everything else is fine. So the question is, can we think about Makai matrices in other worlds? So tensor categories, Hopf algebras. I think even some of the graphs that Martina came up with, like the Bruja graph, can sort of be viewed in the same type of setting. So what I'm going to focus on here, though, is finite-dimensional Hopf algebras over algebraically closed fields of characteristic 0. And I'm going to take a finite-dimensional H module with character chi trace, the trace. And I'm going to take the simple modules. And the first obstacle you sort of run into is that this tensor product may not be completely reducible. And you could think about, well, maybe we should assume that the Hopf algebra is semi-simple and make it completely reducible, but then we sort of are throwing out a lot of really good examples. Examples like quantum groups at roots of unity, restricted enveloping algebras and characteristic P, Drinfeld doubles of Hopf algebras. So I don't think we want to make that type of assumption. Rather, I'm going to let Mij be the multiplicity of Sj as a composition factor of this tensor product. Another thing we could do, another way to sort of think about this is to think in the growth integring. And I have the isomorphism class of Si, the isomorphism class of V. And when I multiply those in the growth integring, I'll be able to write that as an integer combination, non-negative integer combination of this isomorphism classes of the simple modules. And it's exactly these same Mijs. So if we go to the growth integring, it's basically doing the same thing we've been doing because the product in the growth integring is the tensor product. So again, we can think about the Makai matrix. And there was a paper that came out fairly recently on critical groups. And what Grinberg, Huang, and Reiner showed was that if you take the vector of dimensions of simple modules, that is an eigenvector. The eigenvalue is the dimension of V. On the left side, if you take the dimension vector for the projective covers of these modules, you get a left eigenvector. Now, this paper of Grinberg, Huang, and Reiner grew out of a paper that I wrote with Carly Clivens and Vic Reiner. And what we were doing in that paper, we were looking at the Makai matrix and using it to define certain finite dynamical systems where we were doing chip firing. And an important thing in chip firing are these things called critical groups. So this paper of Grinberg, Huang, and Reiner actually grew out of that, but that's another place where sort of Makai matrices come up in sort of a context of chip firing. So ever since I got a copy of this paper by Grinberg, Huang, and Reiner, I started asking Vic Reiner, can't you say anything more about the eigenvectors? Can't you? And he got tired of me. So
we
what I
lost
wanted
you
to
there.
talk about is some joint work. The five of us were at a workshop where the sort of format of the workshop was to work together in groups. So this is a group project. This paper has been posted on the archive if you're interested. So in a Hopf algebra setting, how you get the action of on the tensor product is using the coproduct of the Hopf algebra. And this is just notation. It's symbolic of the coproduct. It's often called Sweedler notation because it first appeared in some work of Sweedler. So I'm going to apply this element X to the tensor product, SI tensor V. And what I get is a sum of products of traces on these factors. And on the other side, I'll just get the multiplicities, the MIJs, the traces of SJ. Now, this vector, well, this equation uses the traces on the simple modules. So I'm going to put those into a vector. This is really a column vector, just trying to save space. And rewrite the equation above. So this left-hand side is coming from the right side up above. And then the right side is coming from the left side above. So if you think about it, this equation is an equation of a column vector on the left to a sum of column vectors on the right. And if you look at the ith coordinate of that column vector, you'll get the equation 2 lines above. So that's all that's going on there. So if you can find some elements of your Hopf algebra where the coproduct is relatively simple, then you might have a chance of getting eigenvectors. And one type of element are these group-like elements where the coproduct is just the product, the tensor product of the element with itself. And in that case, this equation reduces to the same equation we saw before for the groups. And if you set G equal 1, then the trace is just the trace of the dimensions, this trace vector, and you recover the result of Grinberg, Huang, and Reiner. Are there any questions, maybe? Try to answer. So what about projective modules? How do we get them into the picture? So far, they haven't occurred. So let's do something similar to what I was doing with the simple modules, and that is to take the tensor product of one of these projective covers and write it as a sum of projective covers. So when you tensor any projective module with any finite dimensional module, you get a direct sum of indecomposable projectives. And that's what those projective covers are. They're the principal indecomposables, or if you like, they're the projective indecomposables. So we can do exactly what we did before and end up with an equation like this using the tensor product. And I'm going to rewrite it a little bit. I'm going to just interchange these two scalars on the left side, which I did before. And on the right side, I'm going to replace the ij coordinate or ij entry of the matrix Q by the ji entry of the transpose. Okay. I haven't changed anything. Let's take our element X and construct a vector. This time it's a row vector by evaluating the traces of the projective covers on X. And then the right-hand side of the equation 2 lines above will give me the left-hand side of this equation. And the left-hand side will give me the right-hand side. So everything is very similar to what we saw before for the Makai matrix. Again, we can evaluate this at group likes and setting the group like equal to 1, we get the projective dimensions as an eigenvector. There's only one sort of slight problem is these are eigenvectors for a different matrix. Okay, so somehow we have to do a little bit of reconciling. And this fact that we proved is extremely helpful here. So this transpose of this projective Makai matrix is really the Makai matrix of the dual module. And there are similar results that have occurred in a number of different contexts. There's a paper by Mazurchuk where he's with a co-author looking at 2 categories. And there's a very similar result that has a kind of the same flavor as this result, that you can relate projectives and with the dual module. So using that, we can replace this projective transpose with the Makai matrix of the dual module, and then get something similar for putting in group likes and then evaluating at 1. Now, if we had a module that was itself dual, for example, then this would be really making a statement about tensoring with V. And I'm going to go through an example, the example of the quantum group UQSL2 at a root of unity, primitive nth root of unity. This is a finite Hopf algebra. F to the n is 0, e to the n is 0, k to the n is 1. And this example is not in the paper I was referencing. It's also not in a lot of other papers. Okay. So here are the simple modules. They look very much like the simple modules that you know for quantum groups, not roots of unity, simple modules for SL2. But the main difference here is it stops. There are only n of them. And these are the projective covers. So notice here that this last module, this dimension n, is both projective and simple. And this is kind of the analog of the Steinberg module. It behaves very much like the Steinberg module for Chevrolet groups, for algebraic groups. So it plays a very special role here. Chari and Premet in a 1994 paper actually determined all the indecomposable modules for UQSL2. So we're just using the ones that are projective here, the projective indecomposables. So this is what they look like. So at the head is the module VL inside of PL. If you factor out the maximal submodule, which is everything beneath it, these three modules beneath it, then you get PL, or you get VL inside PL. At the foot is the socle. And if you factor out the socle, then you just get the direct sum of two simples. So there's kind of a complementary pair here. You notice this Pn minus 2 minus L. So when the two indices add up to n minus 2, then you get the same composition factors, but they're arranged differently. So when I start looking at multiplicities of composition factors, these two are going to look the same. So the module I'd like to tensor with is the natural module here. And these are the rules for tensoring within. So the first rule is very much like the Klebsch-Gordon rule that you know for SL2. When you get to the end, because when you tensor projective with anything, you get projective, we actually end up with the module over here on the right with L equals 0. So this is Pn minus 2. Incidentally, I think it's interesting if you think about Ivan's lecture yesterday. He had very similar triangles, or diamonds, I should say. The VL was the blue dot. The two middle ones were the pink dots, and the bottom one was a green dot, but they were strung together and connected when he was looking at representations of the affine temporally Lieb algebra. So somehow these are sort of very similar types of structures coming up. What about the Makai matrix? Okay. So the first n-1 lines are exactly this first rule. So if you tensor V0 with V, you'll just get V. That's at 1. And then you get subtract 1, add 1, subtract 1, add 1, all the way down. When you get to the bottom row, what you're looking at are the composition factors of Pn minus 2, which are these two copies of Vn minus 2, which is over here, and two copies of V0. Are there any questions before I continue? So if we look at the roots of the characteristic equation, what they look like are just sums, q to the j plus q to the minus j. Now at j equals 0, that's just 2, which is the dimension of V. So we knew that 2 was going to be an eigenvalue. So that had to show up in the characteristic roots. But sort of what else do you notice about these characteristic roots? Well, if you take j equal 1, or if you take j equal n minus 1, you get the same root. So these roots occur in pairs, and so you have repeated roots. So everything for j not 0 is going to be a repeated root here. Okay. Here's the quiver. So it doesn't exactly look like a quiver, but the only real interesting part is this part where we tensored Vn minus 1 with V and got 2 copies of V0 and 2 copies of Vn minus 2. So what about eigenvectors? So to define or construct the eigenvectors, I'm going to define a family of polynomials. So U0 is 1, U1 of t is t, and then the rest are given by a recursion. Anybody recognize these?
Chebyshev?
Yes. These are Chebyshev polynomials of the second kind. So the eigenvectors we can describe, these are column vectors here, by just taking these Chebyshev polynomials of the second kind and evaluating them at the eigenvalue, the qj plus q to the minus j. And there's a, so this is a right eigenvector with that eigenvalue. There's a very nice formula for these Chebyshev polynomials of the second kind, evaluating them at x plus x inverse. And you get a sum of powers of x. And again, this is looking very much like something in Ivan's lecture, where you have things that start at an integer and then go down by 2 to the negative of that integer. But most of us should think of that as what? Eigenvalues of something. And in fact, this is the trace when I put in for x q to the j, I'm actually getting the eigenvalues of kj, k to the j. And when I add them up, that's the trace of k to the j on VR. So that's another way to think about the eigenvectors. So in fact, this EJ is a trace vector of a group buck. But the main problem here is you don't get enough eigenvectors. We only sort of get half of as many as we need for the J's that are not 0. So these eigenvalues where J is not 0 actually correspond to 2 by 2 Jordan blocks. So before I talk a little bit more about the implications of that, let me just write down what the left eigenvectors are. So they're given by a similar recursion. The only difference is that instead of having 1, like we had for the Chebyshev polynomials of the second kind, we start out at 2. And these polynomials, you can argue very easily that when r is bigger than or equal to 2, they're actually the difference of 2 Chebyshev polynomials of the second kind that are r and r minus 2. So that's quite useful because, in fact, when you plug in x plus x inverse, you just get x to the r plus x to the minus r. So you can see that for r bigger than or equal to 2 from this equation above and this fact over here, because all you're doing is chopping out the middle of this expression. For r equals 0, it's clear because that's this 2. And for r equals 1, it's just t is t. Okay. So that's quite useful in working with these left eigenvectors. And in fact, the left eigenvectors are just these row vectors where you plug in these L's. So this is a left eigenvector for the Makai matrix with eigenvalue q to the j plus q to the minus j. Are there any questions? Anybody like to ask a question? So I thought I'd talk about an application. So this is joint work with Percy Diaconis, Martin Liebig, and Pham Thiep. It appeared a couple months ago in Journal of Algebra. So I'm going to take my Makai matrix and conjugate it by a diagonal matrix that has these dimensions of the simples down the diagonal. So this is an L plus 1 by L plus 1 matrix, but it's just diagonal. It's got these dimensions down the diagonal. And then I'm going to divide by 1 over the dimension of V. So what you can see from this formula is this matrix has eigenvalues that are, they're the eigenvalues of M sub V, except for this factor of 1 over dimension V. And there's really a close connection between what the eigenvectors are. Just move this D inverse over to this side, and you can see. So I'm going to think about this a different way here. This is the transition matrix of a tensor Markov chain. And this entry, this ij entry of this matrix, is the chance of moving from Si to Sj by tensoring with V. So what we're doing here is we're taking our Makai quiver. To each node of the Makai quiver, we assign a probability. It's called the stationary distribution. Essentially, it's made up of kind of products of dimensions of simples, multiplicities that we're getting, and dimensions of what we're tensoring with. And then we're taking powers of k, so we're letting this Markov chain just run, and then saying, when do we get something that's close to this stationary probabilities that we first assigned? And it turns out that these rates of convergence were really difficult to compute. So the paper has lots of examples. A lot of them come from modular representation theory of group. The one example that comes from that example that before with UQSL2 is the most challenging of these. And that's because it has a new feature, Jordan blocks of size 1, greater than 1.
Sorry, Georgia, is the matrix real, or you allow probability to be complex numbers?
These are going to be all rational numbers.
Real ones.
The transition matrix will all be rational numbers.
Thank you.
So Percy has computed just thousands of Markov chains, and he said he's never had to deal with Jordan blocks of size bigger than 1 before. So I think these examples coming from Makai matrices can provide some interesting examples in sort of the probability world. I want to talk about what's sometimes called the fusion matrix. So let's go back to the general context of simple modules, projective covers, the projective covers, and look at something called the Carton Map. So this is actually a map between two growth and deep group rings. So on the left is the growth and deep ring that has an integer basis of these isomorphism classes of these projectives. And on the right is the growth and deep ring that has an integer basis of these isomorphism classes of simple modules. And this map is really taking this projective isomorphism class to itself, but then re-expressing it in terms of the basis of simples. And there's something that people call the Carton Matrix. It's not what you think. Okay, it's just the matrix of this map up here. And I'm going to let M be the rank of this Carton matrix. So in a paper by Cohen and Resrag, they studied this situation. They assumed a lot on the Hopf algebra. They assumed it was quasi-triangular, had a ribbon element. And what they showed was that there's a subset of the projective covers, M of them, which is the rank of this Carton matrix. And you can form a matrix using those M projective covers. So what you're doing is rewriting this tensor product in terms of just the ones that you've listed, and then getting a matrix. And what they showed was that this matrix is diagonalizable for any simple H module. The eigenvectors don't depend on V. And there's what's what you call a Verlinde formula. So there exists a matrix F and scalars such that the conjugation of NV by F gives you a diagonal matrix. And the diagonal matrix are these scalars times the inverses of these dimensions. So these are the dimensions of the simple modules that are connected to these select list of projective covers. Or another way you could think about this is that if you move this F to the right-hand side, this F inverse to the right-hand side, just multiply through on the left by F, then this F is giving you the eigenvectors. And it doesn't matter which V you choose because it doesn't depend on V. So choose something simple. Okay. Actually, they assumed it was a simple module. Just choose something that's very small. So the inspiration to do this comes from a very influential paper of Verlinde in 1988 called Diagonalizing Fusion Rules for Two-Dimensional Conformal Field Theory. So there's something very similar to what they're doing here in this paper of Verlinde. So I want to go back to UQSL2 to that.
I'm sorry, may I ask a question
Sure.
about the previous slide? So what is so special with the modules P tilde? So how do you choose it among the P0, P1, PL?
So you're sort of cutting out redundancies. So I can illustrate it pretty well with the UQSL2 example, but you're just choosing enough to get the rank of the Carton matrix. Then any other one you can get as a combination of these chosen ones. So you're looking, essentially you're looking at the Makai matrix and you're saying, you know, what rows can I get as sums of other rows? And I'm cutting out the ones where I have redundancies.
Okay, thank you.
Yeah, okay. So in the SL2 case, remember that these two modules have the same composition factors. So they're going to have the same image under the Carton map. And so there are differences in the kernel of the Carton map. So what I'm going to do is choose a list of projectives. This list of projectives, if I look at the projective growth integrating, these ones that I've listed are complementary to the kernel of the Carton map, that ideal. And because of this relation with the Carton map, we'll make these identifications. So the difference of these two is in the kernel of the Carton map. So again, I'll choose V to be the two-dimensional module. And this is the matrix that I would get that would be the fusion matrix. So notice when I tensor Vn minus 1 with V, I got Pn minus 2. But I'm identifying that with P0. So I get a 0, 1 here when I use this top list of projectives. When I tensor P0 with V, I get 2 copies of Vn minus 1, which is that 2, and 1 copy of P1. And I just keep going. It's very much like the Clebsch-Gordon formula. But when I get to the end, when I tensor this n minus 3 over 2, 1, I get the one to the left and the one to the right. But the one to the right is the one below, which is the one above. Okay, so that accounts, that accounts for this last row. I got the one to the left and itself. So this would be the analog of the fusion matrix in this UQSL2 setting. And it turns out the eigenvalues are the same. This is diagonalizable. And the right eigenvectors are these L polynomials. And the left eigenvectors are given by polynomials, evaluating polynomials at the eigenvalue that are given by these formulas. So again, this is very much like the Chebyshev polynomials of the second kind. The only difference is this V1. V1 is, instead of being T, is T minus 1. And these are Chebyshev polynomials of the third kind. So these Chebyshev polynomials of the third kind are the difference of 2 consecutive Chebyshev polynomials of the second kind. The L polynomials are the difference of 2 Chebyshev polynomials of the second kind that differ by subscripts 2. So maybe these should be called the Chebyshev polynomials of 3.5 kind. I don't, but anyway, it's amazing how these polynomials are coming up. Maybe some of you have some good explanations for this. I want to make some comments here. The joint paper that we did works all this out for the Drinfeld double of the tapped algebra. And this is an algebra, it's a Hopf algebra, and it has n two-dimensional simple modules, not just one. It's been said that Chebyshev polynomials are everywhere dense in numerical analysis and here too. So all these examples, especially the ones involving two-dimensional simple modules, have always had Chebyshev polynomials all over the place. For Dn, the right eigenvectors are trace vectors of simple modules evaluated group lengths. And this was true also for the UQSL2 example. So you might think, well, maybe looking at trace vectors at simple modules evaluated group lengths is maybe the way to get right eigenvectors for Makai matrices. But there exists Hopf algebras with no group lengths. So even if you require it to have an identity element, you're still only going to get one eigenvector. So that doesn't seem to be the way to go. Even if you restrict to semi-simple Hopf algebras, you can have a situation where you don't get enough eigenvectors from the group lengths. You just don't have enough group length elements. For these Drinfeld doubles, only some of the left eigenvectors are trace vectors of the projective covers at group lengths. Dn is a nice Hopf algebra. It's quasi-triangular. It's a ribbon Hopf algebra. So it does satisfy the hypotheses of the Cohen-Westreit paper. So in our second paper, we use the R matrix and the ribbon element to get a representation of the temporally-Lieb algebra. And this is the same parameter comes up for all of the two-dimensional simple Dn modules. This representation of the temporally-Lieb algebra is injective for all k if you restrict to the unique self-dual two-dimensional simple module. I believe it's injective for all of them, but we don't have a proof. For this one that's self-dual, the centralizer algebra, the Dn action, is the temporally-Lieb algebra up to tensor powers 2n minus 2. And then the centralizer algebra starts to grow very rapidly. So the question is, what is this centralizer algebra? Can you realize it as nice diagrammatics that's like the diagrammatics of the temporally-Lieb algebra, or the ones that Yvonne had yesterday, the affine temporally-Lieb algebra? So that's something to kind of thinking about. Some questions. If you take a finite-dimensional Hopf algebra and a finite-dimensional H module, when is this Makai matrix diagonalizable? Can you put on some assumptions on something, both maybe the Hopf algebra and the finite-dimensional module, that will enable you to say it's diagonalizable? when do n of v and m of v have the same eigenvalues? I mean, it was sort of surprising to us that they did have the same eigenvalues because they're defined so differently. Okay, this is sort of the overarching question, is what's a good notion of a character table for a Hopf algebra? So if you look at a lot of the Hopf algebra literature, when people talk about a character table, they're putting on a lot of different assumptions and using various different things to construct it. So you might put on semi-simple, almost cocommutative, and then use the central primitive idempotence to define the character table. So is there a nice, good, uniform way to construct a character table that may or may not be related to Makai matrices? So stay tuned. Thanks.
Yeah. Thank you, Georgia. Are there some questions for Georgia? Sure. Go ahead, Ivan.
Can we use the Makai matrix or the fusion matrix or any of the matrices that you've defined to compute the decomposition, for example, of a given V with itself, many copy of it?
You could, maybe one thing I could say is in the UQSL2 case, tensoring with V1, if you do repeated tensoring with V1s, you actually will see all the simple modules
Appearing.
And so all the simple modules are, in some sense, a polynomial in powers of V1. And so they'll all have the same eigenvalue vectors because they're polynomials. So that's one place where you could see sort of repeated tensors coming in. Another might be to just start with the trivial module and start tensoring with your V. And then that would be the same thing as sort of looking at kind of, well, maybe even just start with all the simple modules and tensor with V. That would be kind of multiplying by the Makai matrix repeated times. So I think you could get information out of that. Probably pretty helpful information.
Thank you. And thank you for the talk.
You're welcome. So I'd like to try to connect it to your affine temporally Lieb algebra, some examples from that.
Yeah, the fusion rules for temporally Lieb, for projectives and the simples have been computed. They are so similar to yours. It seems that there's a relationship. It's not exactly obvious how it comes out.
I was wondering whether the small quantum group was very, very close to the Scherweil dual of the affine temporally Lieb.
I don't know, maybe Yvonne knows.
Could you repeat that, Michael? Sorry.
I was wondering whether the small quantum group, meaning the finite dimensional quantum group that Georgia is considering in her UQSL2 example, is very close to the centralizer of the affine temporally Lieb. Because that would explain some similarities there.
In the picture, but is there anything special that would occur at something like 2n minus 2? I don't know. That's when it starts to grow.
I was wondering too, Georgia, you assume throughout that you're dealing with finite dimensional Hopf algebras so that your simple modules are finite dimensional. but is that the real reason, or could one work with some infinite dimensional Hopf algebras if one chose carefully some finite set of preferably finite dimensional modules? I'm trying to think of whether one could actually try to get the actual Verlinde formula out of this via Kazhdan-Lustig.
I haven't tried. I don't know. This question of would you truncate it to try to get a finite matrix or something like that?
Yeah, you choose certain representatives.
I should say that that example of UQSL2 is basically the same thing that happens with the restricted enveloping algebra for SL2 in characteristic P. Everything is really
that's encouraging.
the same.
I was thinking about affine Lie algebras with representations of a fixed level and the strange tensor product.
Representations for the affine. Yeah.
Mm-hmm. Yeah. Are there other questions? Okay, well, I thank Georgia again for the excellent talk. And we now have a tea break, or whatever kind of break you like.